All right, we're just sneaking up on 2 o'clock here. Let's just give it one more minute and we'll go ahead and get started. Just as a reminder, feel free to use the Q&A feature of Zoom to ask any questions you have. At the end of this, I'm more than happy to answer any questions you have. I can also be looking at it throughout. Should be a great webinar today, but I don't imagine us taking the whole hour, so feel free to ask as many questions as you want, and we can look at those, or I'll do my best at looking at those as we go. Awesome. Thanks again for joining me today. My name is Ethan Raito, and today we're going to be taking a look at MANTLE'S software and doing a little bit of a deep dive on MANTLE'S software and going in a lot more depth, honestly, than what we currently have online or on our website or have really showed. So if you're here, you're getting a pretty exclusive look into a lot of the features behind our software. I also will be talking about throughout, some of the different parts I have with me here today. So feel free to be looking at the slides as well as my little camera here, because I have some different parts I'll be talking about and talking about some of the toolpaths for these parts specifically. All right, great. Thanks for joining, and let's go ahead and get started. So if you're not familiar with Mantle already, I just want to cover a little bit about the background of Mantle. Mantle's goal is to automate your tool making. We do this by printing precision mold components with unmatched accuracy, surface finish, and tool steel performance. The accuracy, the surface finish, the tool steel performance that are required for these precision mold components. The way we do that and what that allows is that it allows us to eliminate the time and cost associated with many common mold making processes, such as programming, rough milling, and EDM process. Specifically today, we're going to talk a lot about how our technology eliminates that programming step, but all in all, Mantle's goal is to automate your tool making process and eliminate those very, very time-consuming processes that you use today to make production tools. Mantle really offers game-changing speed, cost, and efficiency with really proven results. We'll only look at a couple case studies today because that's not really the focus of this webinar, but with proven results to produce parts in less time, at less cost, and do things that are more efficient, such as conformal cooling and some advanced geometries to allow for more efficient molding processes. Mantle's printer was designed with tooling in mind. We like to say that this is the only metal 3D printer that was designed specifically for printing of tooling. It offers the precision of a CNC machine, the design freedom of a 3D printer, and it's priced and accessible for every single shop. You can see our printer here on the left and our furnace on the right. And I'm going to talk a little bit about how this technology works, because it's very important to understand how our technology works to understand how our software integrates with that. So if you're at all familiar with Mantle's technology, you know that we print a flowable metal paste. That paste has a similar consistency to a toothpaste that you buy at the store. It's a paste, it's flowable. And what that paste is a combination of metal powder, various different particle sizes, powders that can be sourced in the metal injection molding world or the powdered metal world, but metal powder of variable different sizes. We mix that with some binder and some solvents. What's really important here and different about Mantle is those solvents. Those solvents really allow this metal powder to flow, and we just include a little bit of binder to hold the part together throughout the printing process. And I'll talk a little bit about how these binders are actually, how these pastes are actually printed, but important to know that our paste is simply a combination of metal powder and solvent with just a little bit of binder. During the actual printing process, we're just printing our paste through an extrusion nozzle, very similar to the most common 3D printing method out there today, FDM or FFF. We're simply extruding this paste through a nozzle. That solvent allows this material to be easily flowable, and thanks to the solvent as well, we don't have any loose metal powder, so we don't have to worry about those loose metal powders in our environment. The paste is not even being heated here. It's viscous enough that it can simply just be pumped through this nozzle. After every single layer, we're going to dry that layer. That drying step is going to remove all the solvents out of that layer. It's going to firm up the part a little bit. And there's still a little bit of binder left behind just to hold this part together, but we've removed that solvent, and what we've created is a very high green body density. So a part that is almost all metal powder at this stage, which is what's really, really important for our process, is that there's very, very little binder involved, and we have a very, very dense green body. At this point, it kind of has the consistency of a dense foam. And from here, we can come in and actually machine this body. So again, we're build our printer inside of a CNC. So we're able to utilize the printing as well as the CNC machining capabilities of that printer to actually machine the part, improve the surface finish, and actually cut in some features that just wouldn't be possible to print. So really, really great advantages here. This is going to be repeated for every single layer. I'm actually going to go a little bit more in depth here than we normally do. What's actually happening is that every single layer is being milled perfectly flat. Every 10 layers are being contour milled. So generally, we simplify this a little bit for a setting like this and just say that it's repeated every layer. But today, since we're diving into the software, I'm going to give you the full look at how this works. Every layer is being milled perfectly flat. Every 10 layers are being contour milled. And we'll look at some examples of that and how the software looks at that and how the software calculates toolpaths for that. After printing is complete, you have what's called a green body. This is mostly just metal powder, a little bit of binder to hold it together. You put it into the furnace. The furnace is going to heat the part just below the melting temperature of the material. The part's going to shrink a little bit, about less than 9%. The reason we're able to shrink so low compared to other additive methods, so much less than other additive methods, is because of that solvent that we're using. And because we're drying it every layer, that there's very, very little voids in our green body, so it doesn't need to shrink that much to close them. The result is a dense tool steel part. I have a couple with me here today. I don't know if you can hear, but these are dense steel components, 97% above dense, no residual stresses, and great parts that are ready for molding. Just want to quickly show a video of this actual process. You can see printing the paste here. And then, of course, we're going to spend most of the time today on talking about software. And then you can see we're drying that paste to remove those solvents out of the layer. And then we come through and we machine that body. Like I mentioned earlier, we're going to machine every layer perfectly flat. Every 10 layers, we're going to do contour milling like this to refine the features, remove layer lines, and even add features that we just couldn't print. So those steps are going to repeat themselves to build up your part. And this is what we're calling a green part. So that's all happening inside of the printer here. In the furnace, this is a vacuum furnace. You're going to take that entire build plate, you're going to place it into the furnace, and you're going to do your sintering process. Heating elements in an inert environment under vacuum so that you don't have to worry about oxidation or anything like that. Going to get just below the melting temperature of the material. The part's going to shrink a little bit, and you're going to end up with a dense, strong metal part. So this is where we'll start talking a little bit about what's happening inside of the printer. So shaping within the printer, we are using a robo drill style CNC that we're modifying for our process. So we're able to leverage that same tool changer that is used in the CNC industry, which allows us to use a variety of different cutting tools. You can see all those different cutting tools that are on the right. We're able to program for all those different tools automatically. And what's happening is that our software is going to automatically select those best tools for the different features that are being used in the process. You can see we're using some very, very, very small cutting tools in here, 10 thou and 6 thou cutting tools that are so small. I don't have one with me here, but I wouldn't even be able to show it to the camera because of how small these cutting tools are. The reason we're able to use these cutting tools very easily is because there's very, very low cutting forces on these actual tools. What we're machining is essentially a dense foam. It's not a tool steel. So we can use these tools without having to worry about the chatter and the braking issues and all the other challenges that come with using very, very small end mills, because what we're machining is essentially a foam, not a dense tool steel. We're doing that densification process in the furnace. So that's just another great thing to consider, is that this is one of the things that we'll talk about, the software that enables this, but one of the things that's so great about this process is that we're able to use these tiny cutting tools to get some very, very fine features that would take extensive EDM work to produce without having to worry about cutting into a dense tool steel, because it's simply the density of a foam. So looking at how our software looks at this is our software is going to take your part or take your tool or whatever you want to print today, and it's going to break it into slabs. What we define a slab is 10 layers, and each layer is 0.1 millimeters thick. So 10 layers of 0.1 millimeters, a slab is going to be 1 millimeter, or a slab is going to be 10 millimeters thick. Oh, sorry, a slab is 1 millimeter thick. A layer is 0.1 millimeters thick. So you can see on our right here, this part on the right, it's just a simple block, the test block when we were testing out our small cutting tool here. That part is 10 millimeters tall. So it's 10 slabs or 100 layers, because each slab is made up of 10 layers. So you can see, if I were to count all my different colors here, we would see that we have 10 different slabs. And if we're looking at just the gray part down here, you can see that that gray slab is made up of 10 layers that are each 0.1 millimeters tall or 100 microns tall. So as I mentioned before, each layer, each one of these gray layers that you're seeing down here is going to be milled perfectly flat with an end mill. Every slab is going to be contour milled. So that entire gray block that you're seeing down here is going to be contour milled. Every 10 layers, every slab is going to be contour milled. Hopefully I'm not over explaining this, but it took me a little bit of time to understand this the first time I looked at it as well. But to look at this again, as we're building up this part, so I essentially I started on this first yellow layer here where the feature detail starts to come in. So you can see we have a slab here. So this slab has 1 millimeter of depth. So our 6th cutting tool can come in here and start to work away at this. We're only machining a depth of 1 millimeter. So we're able to again, very, very low cutting forces because we don't have to worry about a very, very deep cut because we're simply laying down 10 layers and then contour milling those 10 layers. We're going to do that again, lay down 10 more layers and then come in and contour mill those 10 layers. So we're always going to be keeping a consistent contour milling depth of 1 millimeter. This allows us to do these very, very deep pockets, right? Because we don't have to worry about, can our tool reach in there? Does our tool going to chatter? Is it going to deflect? Because we're always milling very, very small depths because we're laying down layers and alternating between print, machine, print, machine, print, machine. So you can see simply building up our part layer by layer, which is something that's great because this allows us to produce these very, very deep features that have relatively small widths and small aspect ratios. Generally, to produce those features without a process like Mantle would require quite extensive sinker EDM work. You'd have to cut your electrodes and then burn all those into your part, which whenever we're talking to a prospect or a customer, they always are looking to remove or eliminate as much EDM time as possible. So the ability to actually just print in these deep, narrow pockets are very, very possible because we're only contour milling a 1 millimeter of depth at a time, which is very, very interesting. Let's start to talk about Mantle's software a little bit more in detail here. Just want to show, a little bit of just one quick example here and talk about how Mantle adds value, and a big part of that is the actual software part. If you've been following Mantle at all, you'll know that we love this case study that with Nicolay Plastics. It was a core, cavity, and actually one more insert that you could see. Hopefully, you can see my cursor in here. They placed inside of this insert here, but reduced lead time from 6 weeks to 2 weeks, operation time from 180 hours to 12 hours, and they're molding a glass-filled nylon. So great case study. We're not going to focus too much on this today, but the reason they're able to save so much of so much time and so many labor hours is because of all the steps they're able to reduce. A lot of steps involved in creating a precision tool, but they're able to eliminate all those by printing. And one of those steps that they were able to remove is the cam step. The cam step is one that people often take for granted, but you need a highly skilled programmer. You need someone who knows what they're doing, and it's a time-consuming step of the process. So Nicolay felt that with our process, we've removed almost all that labor time involved with the cam step, which is very, very important because traditional cam is complex. It's very, very complex. It has a very, very steep learning curve. It's very, very expensive. When we talk about CAM with our customers or with prospects, they're always saying they have a few programmers that are very, very highly skilled. They're very, very important to the customer because it's not something that anyone can do. That's really talking on the CNC side of things. On the 3D printing side of things, because of course Mantle is a hybrid approach doing both CNC machining and 3D printing, we hear the same thing, that traditional slicing softwares for maybe these laser-based systems are very, very difficult to use. They have steep learning curves. They're expensive. They're challenging. You get some mixed results if you don't, the first few times when you're troubleshooting, that it may take you years to start getting good parts out of your printer because of how you're using the system. We knew that both of these challenges, the last thing that tool shops need and molders need is another piece of equipment that's hard to use. So Mantle really focused on creating a software that was incredibly easy to use. Just to kind of reiterate this point, I went online this morning and I was looking for some training programs for some CAM software. This is a training program that I found that this is just the basic or the essentials of Mastercam, and this is a 4-day in-person class. So just to show, this is certainly not an easy software to use. I know that they're very, very powerful and there's lots they can do and they're critical to the business, but they're not the easiest softwares to use in the world. And Mantle knew that, like I mentioned before, the last thing that tool makers needed was another piece of equipment that's hard to use or another software that was hard to use. So with our software, our promise is that we can generate toolpaths in just minutes, both the additive and subtractive processes. There's no programming required. You'll see today, I'm about to hop into the software and actually walk through some of this. You don't need any CAM experience. I've never worked with CAM before, and I'm able to use our software pretty easily. And you can train users in just minutes, which we'll put to the test today because I'm going to walk you through using our software right after this. So Mantle software was really designed to eliminate all those challenges involved with traditional CAM software and traditional slicers and make this process very, very simple to use. So with that, let's go ahead and jump into the software. I think I need to briefly stop the share here and reshare to ensure that you have visibility of my entire screen. Let's see here. Okay. Hopefully everyone can now see my entire screen and see that we are now in the Mantle software interface. Inside of here, I have a couple different things on the screen, and I'll walk you through what these different things are. But essentially, we have parts, plates, and builds. And today we're going to walk through doing all three of these different things. Of course, a part is pretty simple. It's pretty self-explanatory. A part is a part. It's our tool file. It's our CAD file. Important thing to know that you just need to simply import your CAD file as is. We're going to take care of the scaling. So you're just going to export your CAD file out of your software, either in an STL format or a step format, and then you could go ahead and bring it into our software. So let me go ahead and do that right now. I'm going to go ahead and hit import part. It's going to pop up my screen here. I'm going to click select. I already have my folder set up here. I'm going to select the cavity that I want to print, which is actually the cavity for this fitted insert that we see that I'm showing you here on the screen today. I'm going to go ahead and hit import. I'm going to select the name here. I'll say, let's say webinar. I have to type live here. Webinar demo 1. Hit OK. It's going to go ahead and import that. Luckily, I have decently fast import speed here because it is a mesh file. Awesome. And you can see it populates here. Webinar demo 1, our part's now up here. I'm going to go ahead and import the cavity as well because we're going to want to print both of these at the same time. And I'll show you how to do that. So I probably should say webinar demo cavity. So we know that it's our cavity file. Go ahead, done, and go ahead and import that. And this is just an STL file, but I also could have used a step file. I actually personally prefer steps, lower file size, and let us do the translation. Awesome. Now I have my two parts here. I'm going to go ahead and select it by both my cavity and my core, which I named them, should have named them more properly. And then I'm going to go ahead and create a plate. A plate is essentially a build plate. So this we're now looking at is the build plate inside of our printer. This is the space we have to work within to actually print. You can see that right now my parts are on top of each other. So I'm going to want to go in and actually translate these and move these out of the way. You'll see they turn green when they're good. And now I can see that I've arranged my two parts here on the build to print these side by side. If I wanted to, I could go ahead and let's add in another cavity. Sure, it's going to come in. I'm going to need to go ahead and move this out of the way or move both of these out of the way so I can go ahead and print. But this is my build space. I can print everything on here that I want all together at the same time. One important thing to know, the only real guidance we give here is that our build times are really dependent on height. So we recommend that you do not build things that are very, very short next to something very, very tall because you're not going to get much value. You're going to start to, you'd rather print things that are the same height together rather than something that's very, very small that'll take maybe a few hours than something that will take a few days next to each other. But you can see I can get all my parts in here together. I'm going to go ahead and just remove this last one, and then I will go ahead and put these back. I also have some X and Y availability here, so I'll just set this to 0, so it's in the center. Set this to 0 as well. Great. And then since I'm a perfectionist here, set this to maybe -27. And I'll set this one to 27 so they're symmetric here. Perfect. You wouldn't obviously want to print things very, very far apart from each other because that's just more travel that your tool paths are going to have to do. Your dispensing tools and your cutting tools, et cetera, are going to have to move all the way across to do that. I also have some basic view settings, front view, top view, ortho views, et cetera, if I want to use any of that. Awesome. So now I have my sort of parts that I want to print together on my plate. I'm going to go over to configurations, and here I have a few settings that I actually can choose, but this is all the settings that we really have available, and very, very simple. Our goal was to give you tools that can be used with minimal post-processing, tools that are ready to go. So, if you look at a lot of 3D printing softwares, if you're familiar with Cura or other softwares, you have hundreds, if not thousands, of settings available to you to customize your print. But we know what our customers want are precise, smooth, excellent tool steel property parts. So we have optimized our settings to do that. This is obviously in our infrastructure, so you can see we have a bunch of printers back at our HQ. But if this was your environment, right, you'd have your different printers that you could name yourself down the shop floor. So you can select the different printer you want to be using for this. Have a couple different subtractive strategies here. A lot of these are actually for internal testing. So the customer only has a few of these. For example, I'm going to select the 20 thou subtractive strategy, which means our smallest tool here is going to be that 20 thou tool. I have some different drying strategies. I'm just going to use our standard drying strategies. Again, we are always testing out different things to ensure we have the optimized ones. But for the customer, the standard is just going to be the perfect drying strategy here. Our software is going to automatically scale those parts for you. So I'm going to want to go in here and select our material. Let's go ahead and print this in our H13 material. I want these to be applied to both my parts. So part 1 and part 2, I can have different settings for, but let's look at this additive strategy. Let's go with our detailed additive strategy and just our basic additive path as well. So with that, I've now sort of set up our build, set up our plate. That's really as simple as it is. Those are all the settings I have here. Go ahead and save this. I'll call this, what do we call it? Webinar demo 1. Great. You're going to see it populate in here. This is our plate here that I just saved, and I can go ahead and click begin slicing. I got it. So there's a difference between a build and a plate and a build. A plate I may want to run multiple of. A build is going to be individual jobs that I'm sending to the printer. I could send the same build to the printer multiple times, but I may want to have different builds with different parameters for trying different things, trying different subtractive strategies, or even just different layouts. So I'll go ahead and name my build here, webinar demo build. And this is going to go ahead and kick off its build. That build is going to take probably 30 to 45 minutes. It's going to run in the background. Of course, all of this is running in our cloud infrastructure, but I'm, of course, doing this like a cooking show, right? So I already have our build done here. And this is, after the build is complete, this is what you'd be able to open. You can see I have on the left here a print time. It's going to take 49 hours to print our 2 core and cavity inserts. It's going to take about 350 milliliters of paste. I can actually look in a little bit more detail if I want to look at paste consumption and things like that to kind of see how much paste is being used when. But what I mostly want to look at is these different, what I can actually view here. So if I want, I can take a look first at our millable geometries. So this is what's actually going to be milled within our machine. This is the mesh of what's actually being applied here. You can see inside of here, I have our different cutting strategies that are being used within the printer. So if I go ahead and just turn all of these on and then hit apply, you're going to see all of those go ahead and be built up. And these are all of our different tool paths for each of these different subtractive strategies. So flatland milling with our 1/8 end mill, different flatland strategy with another 1/8 end mill, which is our tool 13 in this instance, our 20 thou ball end mill for waterline milling, our constant cusp milling with the ball end mill, which is our actually shallow cutting that we're doing. And then, of course, the rest of the roughing that's being done with that 20 thou ball end mill as well. I think this looks a little bit complicated, so I'm going to go ahead and turn off that millable strategy. Let's just look at, for example, maybe layers 190 to layers 200 here, and I'll go ahead and apply that. Awesome. So let's look in here a little bit and see what's actually happening. So you can see, these are all my constant cusp tool paths that are being done with that 20 thou ball and mill. This is actually the cutting all the shallow regions of the tool. If I were to, let me just throw on the millable again, you can see, yep, that makes sense. This is cutting all these kind of shallow regions of our tool. Let's see what else is there. We can see our waterline. Waterline is doing everything vertical to the build plate. You can see that makes sense. It's doing all of these sort of outline lines that we're seeing here, all within our tool path as well. Awesome. Let's turn all of these off and look at just the 20 thou. Oh, there's none of that being used here. Maybe we're not using this tool right now. Okay. So interesting thing to show here as well is that this is actually the buildup of our tooling paths. So the different meshes here. So this is showing the simulation of what the part's going to look like after if we just did flatlands milling. Unsurprisingly, you're seeing almost all of the part is outside of deviation. Almost all the part is outside of that 0.1 millimeter deviation that is our baseline here, because this is showing only having used that flatlands 1, which is the very, very basic milling of just cutting in 0. If you look at another the next flatlands, you can see, okay, yeah, now we've come in and all of this top section is within deviation because we've come in with a smaller flat cutting tool that our software decided was better use for this situation and cut all of those surfaces flat. If we look at waterline, which is going to cut everything vertical to the build plate, unsurprisingly, let me just turn off all our meshes. Yep. Unsurprisingly, almost all of the tool is coming within tolerance here and within deviation, except for some of these kind of shallow paths that you're seeing in here. You can see that red in here is still outside of deviation because this is a progressive process. So you can see these corners are still with outside of deviation. You can see those are still with outside of deviation as well. If I go to constant cusp, which is going to do kind of all the shallow regions within the part, we'll see that a lot of that now is within deviation because it was able to go in and machine all those constant cusp. And if I go to the end here, which is just after everything, you can see this is everything that we feel will be within these deviations, but you can see that some of this part is still red. Some of these features are still, out within these levels of deviation. The question here now is that acceptable? Am I okay with my green body being with this level of deviation, that these corners, for example, are sharper than what we are able to print with the cutting tool strategy that we selected? Here we selected a 20 thou strategy. As you can see, I selected my 20 thou strategy up here. So that's why these features are left this way, because those features on this tool are smaller than a 20 thou ball cutter can do. These radiuses are smaller than a 10 thou radius, which the ball cutter would leave behind. So question now is that acceptable? You can see that this is a 48-hour print time for both these inserts. Maybe that's okay. We're going to do an EDM burn anyways because we need these threads to be really, really sharp. If it's not okay, I could go back and I could do another print, or I could do another subtractive strategy. For example, here I did a 6 thou ball end mill. You can see my print time does go from 48 hours up to 55 hours. So I've added 8 hours to the print process because I'm using a smaller end mill now. But you can see all these details in here are much closer in deviation. Sorry, let me just get in here and then stop moving the camera, because now I'm using a small end mill that's much, much closer to that sharp that we need in this instance. If I turn on just that 6 thou subtractive strategy, you can see, unsurprisingly, where are all those tool paths that the 6 thou cutter is using? They're all in these very, very sharp regions. You can see, so like that's, all these sharp regions in here. Let me turn this to. Yes, you can see those are those. Let me turn this off. Those tool paths in those sharp regions just for that 6 thou ball end mill. So you can see this is essentially showing you all those parts of the part that are those very, very rough settings. Can turn all these on just to show you all the different tool paths that are going to be involved here to do this. Can also look briefly just at the facing paths that are going to be involved, and this is just the facing paths that are going to be involved with those larger ball end mills and end mills in general to do those facing steps, every single layer of the process. So again, just to show you, I can look at all of this from here. I would simply send this job to the printer. It's going to go directly to the printer, and I'm ready to go. So in just a couple of minutes, I'm able to prepare a job. It's going to be preparing in the background. I can prepare multiple jobs in the morning. I can go get a cup of coffee. I can come back and they progress pretty far along. If I want to look at these different tool pathing strategies, I can, but pretty simple in what it takes to actually produce these geometries and these tool paths automatically. One other thing to show you, I can show you the actual dispersion. This is the offset of the cutting tool, where it's going to kind of print oversized in here. And you can see that these cutting tools obviously are coming back and cleaning these different strategies up, which is why you're not actually seeing any of the cutting paths, because we're overprinting a little bit, because then we're going to come back and machine them and touch them up. So the millable obviously is quite smaller. The offset's a little bit bigger. Just a couple more things I want to show you. This is some things that are actually coming soon to our software that hopefully now you're seeing the slides again. Let me just double check to see what you're sharing. what I'm sharing. Just want to make sure I'm showing the right thing. Oh, and I should have shown, here's the actual part, of course. This is for a barb and fitting. You can see that, it obviously doesn't come across that well on the webcam. I wish you could see, but these are some really, really sharp threads in here and some really, really nice features and some sharps that were able to be produced with our process. Okay. All right. Couple other things just to show that are parts of the software that are coming. We have a overhead camera within the printer. It's going to take a few pictures every single layer. So for example, it's going to take a picture after you've dispensed. It's going to take a picture after you've come through and faced that layer. It's going to also take a picture of every single contouring layer. This is very, very helpful for the inspection process because if you need to go back and see maybe something went wrong, very, very helpful. It's also incredibly helpful if you were to ever need troubleshooting help from the Mantle team because you could send these images to our team. They can look at them and they can help you troubleshoot if anything went wrong. Why did it go wrong? And I'd be able to help you over the phone because we're able to see all of that within the printer, obviously, when you share it with us. Another very, very cool thing is some printer analytics. This is just looking at one of the printers in our fleet. We can see the status. How long has the printer been up? How long has it been running? How much time is left in the job? For example, this print has 1 day and 2 hours left in the job. This is how much paste is left within the printer, so we can make sure that our printer's not running out of any paste, and we can see our utilization of the printer over a set period of time. So, for example, this was from April 1st through May 7th, and you can see our printer was running at about an 87% utilization, which we feel was excellent for capital equipment and for hardware to ensure you're getting the most out of your technology and your equipment. That's all I have for you today. Hopefully that was helpful. Hopefully that was a little bit of a deep dive into our software and showing you more in depth than really anything we've done so far to date. Hopefully that was valuable. If you have more questions, thoughts, or comments, or there's other things you want to poke around in, feel free to shoot me an email. We can always hop on a call and we can do some of this stuff together and show you more of these features. Hopefully this was valuable for you. But this is thank you for that and let me know if you have any questions. I'll take a look at our questions.